This is Roger Timmerman McLean for Dr. Nasseri's Manufacturing Processes class. This is spring 2011. I'm going to do practice problem number 3 in chapter 4. The problem says glass has a density of 2.5 grams per centimeters cubed at room temperature of 25 degrees. It wants us to determine the density at 1,000 degrees. And it gives us the coefficient of thermal expansion of 6 times 10 to the minus 6 inverse Celsius. Visually, to understand what's going on, excuse me, we've got some volume at 25 degrees and a density of 2.5. We're going to raise the temperature to 1,000 degrees. We want to know what's the new density for that volume. Excuse me. So to understand what's going on, or actually to work this problem, you got to start off with density. And what is density? Just briefly, density is described as mass per unit volume. In other words, density is mass over volume. So in this first instance, mass per unit volume, this idea of unit volume is very important because based on unit volume, we're going to make an assumption. Unit volume means that this volume here, the width, depth, and height are all the same. That's what unit means, like unity. So since the width, depth, and height are the same, what we'll do is we'll just assume that the width right here, marker doesn't work. Assume that our width right here is 1 centimeter. Let's just assume 1 centimeter. So if the width is 1 centimeter, then the depth and the height is going to be 1. And so this volume at 25 degrees is going to be V1 is going to be 1 centimeter cubed, which is going to be 1 centimeter cubed. All right, because this cubed is width times depth times height. So the next thing we're going to do is we're going to look at what exactly is really going on here. And what's going on here is we're going to go from 25 degrees to 1,000 degrees. Basically, to make that change, what we're doing is we're adding heat to this volume, heat energy to this volume. So since we're adding heat energy to this volume, we're not changing the mass. There's no mass to be, the mass isn't being changed. So in this instance, we can call this P rho at 1 mass is equal to volume at 1. And here we can say rho at 2 mass is equal to the volume at 2 over here. And so we know that mass doesn't change, so mass is a constant. So we can rewrite these two equations in terms of mass and say P1 V1 is equal to P2 V2. And actually, that's rho 1 V1 is equal to rho 2 V2. So rho was given to us. Volume we calculated based on our assumptions for 1. So now what's going on in situation number 2? We want to find rho at 2, but we don't know the volume at 2. So how do we find the volume at 2? Well, we've got an equation that tells us the change in this length for a specific change in temperature and given the coefficient of thermal expansion. And that formula is L2 minus L1. So the length here at 2 minus the length here at 1 is equal to the coefficient of thermal expansion, which is given, times L1, this original length here, which we assumed was 1 centimeter, times the change in temperature. So this equation right here will tell us what this L2 is. So if we read this L2 here, tell us what that is. So if we rewrite this equation, let's move L1 over, we get L2 is equal to coefficient of thermal expansion times L1 times the change in temperature plus L1. Now, why do we want to find this L2? Well, we want to find L2 because we know, once again, going back to this idea of unit volume, that if we know what L2 is, we're going to know what the other dimensions are here. They're going to be the same. And so if we know what this L2 is, and we know then we know the depth, and we know the height, And so we know what we can figure out what V2 is. So all this information is given. We can solve for L2 here. Let me just plug this in. L2 is going to be equal to 6 times 10 to the minus 6 times 1 centimeter. I'm not going to put in my units just for space because we realize that we're working in all centimeters and grams, so units are going to work out. So in this situation, I won't specify my units because I know they're just for space purposes. Change in temperature, this is going to be 975 plus 1. So solve for L2. L2 is going to be equal to 1.00585 centimeters. All right. So we know L2, so we can figure out what V2 is. So V2 is just going to be L2 times L2 times L2, because L2, this is actually the height and the width, and we know they're all equal. So probably more accurate way to say this would be just L2 squared, L2 cubed. So V2 is going to equal to 1.0175 centimeters cubed. So going back here, like we already know this was given, rho 1 was given, volume at 1 we got from our assumption, that's equal to rho 2, which we're trying to find is density at 2, times this volume, which we just found, the volume at 2, which we just found based on this equation, on the relationship between change in temperature and this coefficient of thermal expansion. So basically we've got everything to solve for P2 now, for rho 2 now. So that's going to be rho 1, V1 is equal to V2. And if we plug in, for rho 2 is going to be equal to 2.5 times 1 over 1.0176. And so here we go. This will give us our rho 2. Make sure you can see this here. I'll write it down here. Rho 2 is equal to 2.4566 grams centimeters cubed. All right, see that? Now we can do a little check just to make sure we're right. We know that if you raise the temperature, you got some volume, you raise the temperature, the density is going to go down. So we know we raise the temperature. We started out with a density of 2.5. We raise the temperature. Now we've got an answer here that says the density rho 2 is equal to 2.456. So it did go down. So yeah, we can feel comfortable our answer is right because logically, there's a check there. So that's it for this problem. Hopefully this explains it and clears up any questions you might have had.